All right, next in our catalog of contact forces will be tension. Which we will designate as T. Tension we can think of in terms of the spring force model as well. Tension exists in things like ropes, chains, tendons, muscles, uh, strings, stuff like that. And the way you can think about tension is, let's say I have a wall and I have a rope attached to the wall. There's my rope. Then I have an object on the other end. Let's say I pull that object this way. But what's going to happen is the rope's going to straighten out, right? And if I was to zoom in on the rope and look at it at kind of a molecular atom level, what I would see is inside the rope, here's an atom, here's an atom, here's the bond between them. Well, I would have, in pulling the rope, elongated the rope, meaning the spring between each of the atoms within the rope would have been expanded. And so what we know then is that within the rope, there would be a force. On this object, I pulled it to the right, there would be a spring force trying to pull it back to its equilibrium position. And for this object, I'd have the same thing. There'd be a spring force attempting to restore it to its equilibrium position. So if you then expand from this kind of small scale, atom scale, to the overall extended object, then the way tension works is it creates forces on both ends of the rope that point towards the center of the rope. And so simplified as a rule that we can use is tension will always point along a rope or a string or whatever, along the rope, string, whatever, in the direction away from the object. That is the object in contact with the rope, string, whatever. So a few examples here. I can have a block, I can have a rope attached to it, and on the other end, I can pull the rope that way. In this case, on both ends of the rope, I would have tension forces that point away from the objects towards the center of the rope. So on the object attached to the left end of the rope, I made a free body diagram, there would be a tension pointing right in this case. For my hand side of the rope, for this side of the rope, there would be a tension that points to the left. These two tensions will always be equal to each other, meaning the tension on one end of a rope is equal to the tension on the other end of the rope. The rope just relays the force from one side to the other. If instead, let's say I had a car, there's my car, and I had a chain attached to it, and the chain was up at an angle like that, and we were pulling on that end of the chain, then in that case, if I was to make a free body diagram for the car, the dot represents the car, which has some mass. This is horizontal. There's some angle. Then in my free body diagram, I would be applying a tension at that angle because the tension has to point in the direction of the rope. That is pretty much it for tension. So often to find the size of a tension, you have to do it using these free body diagrams and your knowledge of the acceleration of the object or the lack thereof, or you simply have to be told the size of the tension that's being applied.